So I'll get going to this. So I'm going to run through the highlights sort of chapter 3 in Griffiths E&M textbook. For the most part, chapter 3 it talks a lot about potential for the most part. You're mostly calculating potential because potential is very useful for calculating more or less everything else related to electric fields. But for the most part, chapter 3 is a mathematical technique chapter. So bear with me while I get used to writing like this again. It's been a while. So this is chapter 3, and this chapter is just called Special Techniques. Oops. And as I said, for the most part, we're just going to be trying to do various things to find potential V. And so far, probably what you've talked about in terms of how we find the potential for things is to do like sort of the direct integration. So if I have sort of a region of charge here, and I want to find the potential at a point P, I sort of take a little chunk of that, and I call that dq. So I take a little tiny piece of that charge, and I figure out the potential at point P due to that little piece of charge. And then since potential is a scalar, you don't have to worry about vectors, you just add them all up. And so when we add them all up, since we're adding up a whole bunch of tiny little pieces, the total potential at a point is just 1 over 4 pi epsilon naught dq over this script r, right? So essentially I'm just adding up all the contributions to the potential over this entire kind of region, right? One thing that we're going to use shortly, and I think you guys probably talked about this a little bit, but Griffiths is great about most things related to E&M, except for this script R. I really hate script R personally. And the reason for that is that this script R, I think you guys have talked about, is really talking about two different vectors. So if I have my charge Q right here, and my point P right here, and what we know is that script R is the vector that points from here to here. Sorry, that's not a nice straight line there, but that's script R. And so when we're talking about what script R is referring to, what we're really thinking about is this vector, which is sort of regular R, not script, just regular R, and this vector, which is what we usually refer to as R prime. And so if I were to add these up, if I were to add vectors, remember that you can add vectors head to tail. So if I were to add, we can see R prime goes to the tail of script R, and then that goes to P. And so this kind of tells me that, this kind of tells me that my vector R is equal to script R plus, too many R's, is script R plus R prime, right? That little kind of vector addition there, right? And so all that tells me then is that script R is R minus R prime, right? So you guys have mentioned that a little bit before, right? Mm-hmm. And so the reason I'm bringing that back up is because when you're doing this integration, the direct integration for this sort of thing, and even when we're dealing with point charges, sometimes it's a lot easier to use R and R prime. It's a lot easier to use two vectors than just the one, because the R is what we call the field point, and that is where we would like to know, in this case, the potential, but it's called the field point because it's mostly, when we want to know the electric field. But in this case, it's where we want to know the potential. And then R prime is what we call the source point. And this is the location of where the charge is, or in this case, since we're integrating, it's where dq is. Where is that little piece of charge that I picked out? And so both of them are vectors. I can write out r and r prime using things like ijk or r theta phi, and I get those vectors. And then if I just subtract them, then I get script r. And that process of doing it in 2 steps is a lot easier than trying to just go right for script r. Usually that will be an extra step that will make your life a little bit easier. So anyway, I wanted to just highlight that, but then as soon as we look at this direct integration, we can imagine that there's going to be lots of situations where I have a bunch of charge together and I'm trying to find the potential, but maybe it's just too difficult to integrate, right? So we would say this is the kind of integral form where I have some charge and I'm trying to get the potential, but we can sort of rewrite this using the differential form instead. So that just means instead of using integrals, we're going to use derivatives. So the first kind of hack that we're going to use here is to use this differential form. And it just means that instead of taking a derivative, I'm going to take this del squared v, the second derivative sort of the potential, and it's going to be negative rho over epsilon naught. Have you guys talked about del squared? So del, again, just being sort of the 3-dimensional derivative here. And then this rho is the volume charge density. Right? And so this equation here, this is called Poisson's equation. And Poisson's equation says if I have some charge density, like a volume charge density rho, I can set up a differential equation, an equation that has some derivatives in it, and figure out what the potential is due to that charge density. Now there's sort of another version of this that is del squared v equals 0. And this is the same kind of equation, but this is telling us the potential. It gives us the potential in regions where there is no charge. And so if you think about it, if I have a point charge, I need to use Poisson's equation sort of right around the point charge, but everywhere else there is not any charge. And so what we're going to find is that if I know the potential at certain points and there's no charges inside this region, that this other equation called Laplace's equation is actually going to be more useful. So Laplace sort of applies everywhere. We use Poisson if there's specifically a charge at that spot.